Hi everybody, it's Ajanette and I am here to cover your Chapter 13 lecture on analysis of variance. So let me go ahead and share my screen and then I will open up that lecture. So what we're going to focus on, this is actually part 2 of Chapter 13. Part 1 focused on repeated measures ANOVA and part 2 is going to focus on a two-way ANOVA. I'm going to go ahead and leave it in this view instead of launching it into the presentation view because Zoom doesn't react well when it's in the presentation view. So I'm going to leave it here. So we've studied one-way ANOVA and we know that one-way ANOVA corresponds to a single factor design where you only have one independent variable, and that can either be a between subjects or a within subjects design. If it's a between subjects, there are different people in each group or each condition, and therefore we do an independent measures ANOVA. If it is a within subjects design, the same people are in each group and they are being measured repeatedly and under the different conditions or over time. And so therefore we use a repeated measures one-way ANOVA. So it's really important you understand when there's only one independent variable, we use a one-way ANOVA. You have to determine whether it's between or within to determine if it's independent measures or repeated measures. But if there are two independent variables being examined, then we need to use a two-way ANOVA or a two-factor ANOVA. The simplest two-factor ANOVA is an independent measures. And so we are going to focus on the simplest factorial design, which is a two-way independent measures ANOVA where there's different people in each group. And what we want to do with all research, we're examining that relationship between the IV and DV, right? But when we have two independent variables, now we're not just looking at the effect of independent variable 1 on the DV and the effect of independent variable 2 on the DV, but we're also looking at how those independent variables influence one another to create different outcomes in the dependent variable. So we isolate the effect of each independent variable and we call those main effects. And then we look at the interactive or combined effect of those two variables. So a two-way ANOVA really lets us answer much more. It lets us answer more questions, and there's much richer analysis involved because very rarely do we develop in isolation in bubbles and vacuums. We never do, right? So very rarely is it just one independent variable influencing an outcome. Most of the time, a lot of things are interacting and creating additional complexity to shape the outcome. And so that's what we want to look at. We want to look at that kind of simultaneous, concurrent interaction between multiple variables and how that shapes the dependent variable. So to be honest with you, although the bulk of our class has really focused on one independent variable and one dependent variable, know that this is a very basic introductory statistics class. In more advanced classes, you'll learn how to focus on techniques that utilize more than one independent variable as a regular practice and more than one dependent variable. And quite honestly, in research, most research involves at least two or more independent variables. And we're examining the relationships between those variables and their combined effects on dependent variables. So when we do have two or more variables, we call those factorial designs. So we had a single factor design for a one-way and factorial designs when we're looking at two or more independent variables or factors. So we're going to focus on the very simplest form down here, which is a two-factor independent measures equal in design. And by equal in, we mean that the number of participants in each condition is equal. Okay? So let's talk a little bit about what that might look like, okay? So we have a research study and it's investigating the role of self-esteem and audience presence on exam performance. So I have two different variables or factors there. I have self-esteem, which can either be low or high. There's two conditions. And then I have audience condition, which is either without an audience or with an audience. And that's two conditions. So I have one independent variable, low or high self-esteem, and then I have a second independent variable, which is with or without an audience. And I want to look at how does that affect exam performance. What that does is that creates what we call a 2x2 matrix. So the number of digits tells us how many IVs we have or how many factors we have. And then each digit itself tells me how many levels or conditions we have per factor. So in this case, this is a 2x2. There's two digits in that equation. So therefore, I know there's two separate factors or independent variables that we're going to be examining in this study. And then because this first number is a 2, I know that there are two conditions for the first factor. And then the other number is a 2. So I also know there's two conditions in the next factor. And as I mentioned, this is the most basic, simple two-way ANOVA we can do. It can be a 2x3, it can be a 2x4, it can be a 3x4, it can be a 6x8. The more conditions you have, the more complex the analysis. And the more independent variables you have, the more complex the analysis. So it becomes exponentially more complicated when you have more than two independent variables and when either of those factors has more than two conditions, okay? When you are looking at the equation that corresponds to the research design, you can literally multiply the numbers times one another, and that tells you how many total conditions you have in a study. So in this case, 2 times 2 is 4. We have a total of 4 separate groups or 4 separate conditions in the overall study. And I'll show you in a matrix in just a bit. So with this two-factor ANOVA, not only can we answer a question about one single IV, but what we can do is we can isolate each of the IVs and say what is the main effect of self-esteem on exam score, and then what is the effect of audience condition on exam performance, and then finally, what is that interactive or combined effect of those two independent variables on exam performance? So it lets us answer 3 questions. Does the individual IV affect the DV? So is there a main effect of IV1 or factor A on the DV? So does self-esteem affect exam scores? Or is there a main effect of self-esteem? Then we can ask, does audience condition affect exam scores? Or is there a main effect of audience status on exam scores? So basically what we're asking is there a significant difference in exam scores between high and low self-esteem individuals? Is there a significant difference in exam scores between individuals who take an exam with an audience versus those who take it without an audience? And then finally, our third question is there a significant effect on the DV of the two IVs acting in combination? Or is there a significant interaction between those two IVs? So we are asking, is test performance affected by the combination of self-esteem and audience? Or does performance in one treatment condition depend on the level of the other treatment? So, so does the effect of factor A depend on the condition of factor B or the level of factor B? Or do those two variables interact to shape different outcomes based on different conditions or levels? And we'll talk about that more because it's complex without actual samples to look at, okay? So here we are illustrating what a 2x2 matrix looks like visually. So we have over here, factor A is self-esteem. They can either be in a low or high condition. And then factor B is audience condition. They can be a no audience versus an audience. So the scores that you put here are going to be individuals with low self-esteem in the no audience condition. Over here, it's going to be low self-esteem with an audience. Over here, it's going to be high self-esteem, no audience, and then high self-esteem with audience, okay? So notice that we have one factor with two conditions, one factor with two conditions, 2 by 2, so 2 times 2 equals 4 separate groups, 4 separate conditions, okay? Because this is a between subjects design or an independent measures, we know these are different people in each group, okay? Okay, so we're comparing the people with low self-esteem to high, we're comparing the people with no audience to audience, and we're comparing the people with low no audience to low audience and high no audience to high audience, and then these to one another as well, okay? So when we look at a two-way ANOVA, we actually have 3 hypotheses and 3 separate F ratios or F scores. So we actually are running 3 separate tests. We are going to run one test for each of the main effects, and then you're going to run one test for the interaction. When we look at the main effects, I'm going to go back. We're looking at what are the mean differences. So a main effect is just acting as if we only have one variable and the other variable doesn't exist. So it would be looking at factor A. We're just comparing all of the people with low self-esteem to all of the people with high self-esteem. And we get a mean for low self-esteem and a mean for high self-esteem. And we look at those two mean differences. And we say, is there a main effect of self-esteem on exam scores? Do people differ significantly in exam scores, depending upon whether they have low self-esteem or high self-esteem? And then for the main effect of factor B, again, we're looking at all the no audience compared to all the audience. And we're saying, is there a main effect of audience on exam scores? Or is there a significant difference in the means for those who have no audience compared to the means of those that do have audiences? So what this is saying is it's saying that our main effects are being analyzed by looking at those mean differences for those larger categories. And each individual factor is analyzed independent of the other. So we literally act like there was never a second variable, and we just compare those overall means, or what we call those marginal means. And so each factor has its own hypothesis. They have a null and an alternate. And when you look at the null, it actually is stating your hypotheses are written in terms of your population parameters. And so we're saying no difference exists between A, that's our first factor, A1 and A2. So there's 2 conditions. So A1 condition and A2 condition. No differences exist. The alternate is saying that they are not the same, so differences do exist. In our hypotheses for a mean effect for B, now we're focused on the means for B1 compared to the means for B2. Our null is saying there's no differences between those means, so they are equal. And then our alternate is saying, no, they're not equal, there are differences, okay? Okay, so now we're gonna look at how do you interpret an interaction? What does the interaction ask? The interaction is telling us that the mean differences between treatment conditions are different from what would be predicted than what you see in the overall main effects, okay? So if my main effect is saying, no, there's no differences in low and high self-esteem, and I actually find out, yeah, there are. When you have an audience preference or an audience present, people with low self-esteem don't do as well, okay? Then that's gonna be an interaction. So maybe I'm showing low and high self-esteem doesn't matter as a main effect, but all of a sudden in the interaction, it seems to matter for people with low self-esteem, but for in the audience condition, but not for the audience, but not for the no audience condition. That's an interaction. So an interaction is telling us that our outcomes with the interactions are different than what we see in the main effects, or that the effect of one factor depends on the effect of another, or on the level of another, excuse me. So let's say the effect of audience condition doesn't really matter. Exam scores are the same for no audience versus audience, but only for people with high self-esteem. For low self-esteem, that's not the case. Or the effect of esteem matters, depends on the audience condition. The effective, there's no differences for self-esteem in the no audience condition, but there are differences in the audience condition. And that's telling me there's an interaction when the effect of one variable is dependent upon the level or condition of another, okay? And so now I'm gonna move into understanding a little bit about kind of what that looks like visually, okay? So we have two hypotheses for our interaction. And just like everything else, we have a null that says there's no interaction, you know, there's nothing significant. And then we have an alternate that says, no, wait, there is a significant interaction between factors A and B. And when we look at a graph and we actually do means plots for our scores, what we see is each different group has a line. So this particular graph is showing low self-esteem on the top, high self-esteem on the bottom. And then this score is what these groups scored in the no audience condition and what these scores are what these groups scored in the audience condition. And we can see that for both groups in the no audience condition, they scored lower. Oh, excuse me, it's measuring errors. It's not measuring their score. So what it's showing is they made fewer errors, both groups, whether you had low or high, they made fewer errors in the no audience condition, and both groups made errors in the audience condition. So what we want to know is is there a significant difference in the overall means between low and high for our main effect? Is there an overall difference between the means of no audience and audience for our main effect? And then for an interaction, does the pattern of those means change? And looking at this visually helps us. If we see parallel lines, the patterns are the same for the conditions. Here we both see no audience is lower than audience. And here we see that low self-esteem makes more errors than high self-esteem, regardless of audience condition. And we also see audience making more errors than no audience, regardless of self-esteem. So the pattern's not changing. Now notice here, it shifts. It's saying, wait, in this case, look at the no audience seemed pretty similar. They weren't very different. But all of a sudden, the audience, low self-esteem mattered. It made a huge difference, and they made significantly more errors than the high self-esteem. So this actually might be showing a significant interaction where we're looking at lines that could potentially cross or diverge from one another, indicating that, that it does seem that the effect of audience depends on the type of self-esteem, such that audience presence did not impact those with a high self-esteem, but created a significant difference in those with low self-esteem, specifically increasing the error rate for those with low self-esteem. Does that make sense? So notice that the interaction is showing us that the pattern changes now based on a level of a second condition, okay? Okay, so let's start to look at this mathematically and look at the formulas. So again, we're doing 3 different F-tests, one that's testing the main effect of factor A, one that's testing the main effect of factor B, and then one that's testing the interaction between A and B. We do a separate F-test or ANOVA for each of those 3 separate tests. And the results are independent of one another. So you have a number of possible outcomes. You can have none of them significant. You can have all 3 of them significant. You can have 1 significant and not the other 2. You can have 2 significant and not the other 1 in any combination. So there's like 8 or 9 different possible outcomes of results. And know that the main effect being significant is independent of the interaction. But when you do have a significant interaction, you have to be careful about how you interpret the main effect of the other variable, because the variable then depends on the presence of the other variable. So it's not independent, it's not isolated. It seems to interact and combine with other variables to impact the dependent variable or the outcome. Our formula for each of these 3 F-tests is the same pretty much conceptually. We're looking at mean differences between treatments as our numerator, and our denominator is looking at kind of that error variance or that within group variance. So similar to a repeated measures ANOVA, we have to do a second stage. Remember that when we dissected a repeated measures, our between groups was our numerator, and then we further dissected the within treatment variance, and we separated that out from between subjects, right? And the individual differences that exist between subjects, and then the error variance. So we dissected that out, or residual variance. But now for an ANOVA, we're dissecting out that between groups variance further. And we're dividing it between what's the variance because of factor A, what's the variance or differences between the 2 groups for factor B, and then what's that interaction variance. So it's a multi-step process. In the first stage, it still stays as the independent samples ANOVA. We still are computing all the same things, but in that second stage now we're partitioning and dissecting and analyzing that between treatments variance and the sum of squared deviations for factor A, factor B, and then the interaction, the combined variance between A and B. And and so what happens then is we have our corresponding formulas, right? Each test has a different F score. So for a main effect for A, it's going to be the mean squared of A divided by the mean squared within. For B, it's going to be the mean squared of B divided by mean squared within. And then for the interaction, it's the mean squared of A by B divided by within. How do we calculate within? It's sum of squares within divided by degrees of freedom within. How do we calculate mean squared for A, mean squared for B, and mean squared by A by B? We do sum of square of A divided by degrees of freedom of A, sum of square of B divided by degrees of freedom of B, and so on and so forth. Then we want to look at, okay, well, how do we calculate our various degrees of freedom? And so here's your formulas for our total, our within treatments, our between treatments, our degrees of freedom for A, which tells us the number of rows in our matrix, degrees of freedom for B, which is the number of columns in our matrix, and then our degrees of freedom for error. And then additionally, here are our formulas for sum of square of A, B, and then A by B. And then here are sum of squares total, our between treatment, and our within treatment formula. So I just started at the F values themselves and worked my way backwards, okay? When you're actually doing the math, you're going to start up here and start with your sum of squared total between treatments and within treatments, and then progress forward, okay? Our 2-factor ANOVA through SPSS will produce what's called a source table. If we do this manually, we can actually create our own source table as well. But we plug in, these are really important from a research standpoint. Whenever you're presenting research where you utilized an ANOVA, it's important to create a source table and embed that into your research. But you put the source of the variant, so you're between treatments, you're within treatments, and your total. And then you are going to break up your between treatments for factor A, B, and then the interaction. So here's your sum of squared deviation values, your corresponding degrees of freedom values, your mean squared values, and then your F ratios. And then what we've done is we indicate which F ratio is significant. This one is significant at a 0.05 level, and this is significant at a 0.01 level. So one asterisk means 0.05 and the other asterisk means 0.02, or excuse me, 0.01. Okay, and this is the standard information that's included in every source table, and source tables correspond to ANOVA. Okay, and I think we talked about that back in chapter 12 too. Okay, finally, when you do have, well, no, I shouldn't say finally, but when you do have a significant ANOVA or F test, you have to follow up with effect size. And the effect size tells us the magnitude of that treatment effect. So for a 2-factor ANOVA, we use an eta squared, partial eta squared. And you do 1 for factor A, 1 for factor B, and 1 for the interaction. And then when we report this, we end up reporting our results template where we say whether each one was significant. So we do 1 results for the main effect of A, 1 results for the main effect of B, and then 1 results for the interaction. And with each one, you have to do a statement of significance, a statistical evidence, a statement of interpretation, and then your descriptive stats. If it is significant, you need to make sure you're reporting your effect size. And so up here, when I'm looking at this, I use my degrees of freedom for factor A and my within. So notice it's 1 in 20. And then I'm gonna do the same thing for B, 1 in 20, and then A by B is 1 in 20. And the reason that these are all the same is because it's a 2 by 2. But if it's a 2 by 3, these are going to change, okay? They're going to be different from one another. But because both factors have the same number of conditions, those degrees of freedom end up being the same, okay? And our error or within treatments is going to depend on our sample size, okay? Okay, so, and make sure you adhere to the template that I post on the course shell as well. And that will take you through how to report these, okay? In terms of interpreting the results, as I mentioned, if in fact, because keep in mind you're conducting 3 separate tests, but they may not be independent of one another. Once, if your interaction is significant, now all of a sudden it's showing that that variable is influenced by other variables. So we want to be cautious about how we interpret the main effect of a factor if in fact it shows that there's a significant interaction, because now that factor is impacted or influenced by another factor. And so the effect of that factor changes based upon the presence and levels of the other factor. So we don't want to put too much focus and emphasis on a significant main effect when in fact the interaction is significant. Because remember, main effects look at the individual or isolated impact of that factor on the DV, but when it's showing that there's a significant interaction, well, now we're seeing it's not an independent effect. It in fact is interconnected and related to the other factor, okay? And so we have to really pay attention when we have a significant interaction, and we need to kind of look at what's happening with the data. How are the patterns shifting? What's changing? What does this mean for the main effects? And we have to start thinking about, why is this data important as researchers? What is it saying to us? What else could be some explanations for this data? And it usually takes a lot of practice. So I post multiple examples of ANOVA, both within your Canvas course shell, as well as in our class activities, we do multiple examples. It's really important to make sure if you weren't able to join us through those lab sessions, that you go back and look at what's posted, because you really need to be able to practice on explaining an interaction. And this is critical, and it will be a larger portion of your grade on the final, okay? So when we're talking about assumptions, which is the criteria that has to be met for the interpretation, for the validity of utilizing that particular statistical technique, then we have to meet these observations, or meet these assumptions. So the first one, as always, is independent observation. So each sample has to be independent of one another. Also, we're assuming that they're normal populations from which we drew the samples. And then finally, we're assuming that there's homogeneity of variance between each condition, okay? So the low self-esteem and the high self-esteem have similar variances, and the with audience and without audience have similar variances, okay? And in terms of how we actually calculate these, the best thing to do is to use SPSS. Very rarely do you do these by hand. Some institutions use R or PSPP, but most institutions, particularly our closest neighboring UCs and CSUs, they do rely heavily on SPSS. So I've listed out your instructions for your data entry. They're going to be in stacked format, remembering that each row represents one participant. So you tell me what was the condition that they were in for factor A, what was the condition for factor B, and then what was their dependent variable score. So you're going to have 3 columns with 3 different variables, factor A, factor B, and then your DV. And then you're going to enter your data and run your data following the instructions provided. And then you're going to then look at your output and determine, is there a main effect for A, a main effect for B, and is there a significant interaction? So in this case, this particular study is looking at 2 different conditions. It's looking at gender with 2 conditions, 2 different factors. It's looking at gender and course type, and it's looking at the effect of gender on final course grade and the effect of course type on final course grade. So do males or females do better in the course? So that's the main effect of gender. Do online or face-to-face students do better in the course? That's the main effect of type of course. And then it can look at the interaction between those 2 independent variables by examining, does the effect of type of course depend on gender? Maybe it matters for men but not women. Or does the effect of gender depend on the type of course? Maybe men do better than women in online courses, but women do better than men in face-to-face courses, okay? So we would still use the hypothesis testing, where we state our hypotheses and our alpha level. We do that for each of the 3 research questions. Locate the critical region, run the analysis in SPSS instead of manually calculating it, and then make a decision based on that SPSS output. So I actually have a video and some materials posted on Canvas that will allow you to see what the results are for this particular data set. Feel free to run it yourself in SPSS, see if you get the same results, but here are sample results paragraphs written for this particular data set. So feel free to run it and see and do it all on your own, and then come back and double check and see if you got the same results that are reported here. And the output is actually, for your reference, it's actually in Canvas under the activity for a 2-way ANOVA, okay? So let me know if you have any questions. Otherwise, I hope that this makes sense. I did provide an extra supplemental presentation on 2-way ANOVAs with a corresponding video lecture if that helps as well. So I wish you the best. We'll look forward to seeing you in lab and practicing two-way ANOVA a little bit more. Okay, bye.